Okay, so now we can relate the linear and angular kinematics here. So if you consider this body here, which may be rotating about a fixed position here, and a point P here on this body will be making a circle. This is our XY position here, and this is our point P. Now we know that the velocity of this point P will be tangent to this circle. So we this is our V here, and this is angle theta, and the distance from here to here is S here, and the body will be moving with some angular velocity here. So now the thing is, how do we find a linear speed and acceleration of a particle of a particular point in the rotating rigid body? So when the rigid body rotates about a fixed axis, every particle in the body moves in a circular path that lies in the plane perpendicular to the axis and is centered on the axis here. So a particle speed is directly proportional to the body angular velocity for a particle P. So we know that S is equal to R theta here. So this S is equal to, here R is the radius of this circle here. And now we take the time derivative of this this equation here, and noting this R is constant for any specific particle, and take the absolute value of both sides. So this what will happen, that ds over dt will be equal to R d theta by dt here. And if we just take the positive value, we don't need to worry about the negative values of the velocities and angular velocities here. So this means that ds by dt is just v and r, and d theta by dt is just omega. So here what we write is that this v can be right in term of the omega. So v is equal to r omega here. Okay, now similarly about the acceleration. So linear acceleration in rigid body motion or rotation. So we can represent the acceleration a of a particle moving in a circle in terms of its centripetal and tangential component. So as you can see that this acceleration of this particle, which is p, can be represented into two components. One is in the tangential direction, one is in the radial direction. The radial component is centripetal component, and the tangential component is what we call is the tangent component, which is in the direction of the velocity here. So the tangential component of the acceleration, which is a tangent, is parallel to the instantaneous velocity, act to change the magnitude of the particle's velocity. So the main contribution of this a tangential is to change the magnitude of the velocity here, which is speed, and is equal to the rate of change of speed. So if you want to calculate this a tangential, which is the tangent component of this this a, is just equal to dv by dt, so which is just the change in speed. And we know that v is equal to r omega, so we can write this dt and then r omega. And because r is constant, so we will write this r d omega divided by dt, which is r alpha. So this means that a tangent is equal to r alpha, and alpha here is the angular acceleration here. So a tangential is equal to r alpha here. Okay, now to find out the a radial or a centripetal, first we need to understand what are these a tangential and a radial will do. So as you can see in this figure here, in this figure, a body is moving on a circle, and the body velocity is shown by this green arrow here, which is tangent to the circle. And in this case, the acceleration of the body is in this direction here. And again, it can be split into two components. One is the tangential component and one is the radial component. Now the tangential component here is in the direction of the velocity. This means that the velocity is increasing. In this case, the tangential component is in the opposite direction to the velocity. So this means that the speed of the car is decreasing. And in this case, there is no component of acceleration in the velocity direction. So this means that the velocity will remain the same. The speed of the car is not changing. The only component of the velocity here is this radial component, which will change the direction of the velocity here. So as you can see in this case here, what we will do, we will just consider that the body is again moving on a straight circular path here, and if it is at position P1 initially, and then it moved to position P2. So this is the center of the circle here, and if this angle is delta pi here, and we know that the velocity v1 is here and velocity v2 is here. The velocity is always constant, always tangent to uh, the circle here. And now assume that there is no angular, there is no tangential component of acceleration. So the v1 will be equal to v2, but only their direction is different here. So if you just draw these velocity v1, and you draw the v2 here, so this is our v1, this is our v2, this is our delta v. And if we just represent this by delta s here, so if this distance is very small, so we can represent this by delta s. And again, we can see that if v1 and this is v2, so this means that this is again delta pi, because these velocities are uh, perpendicular to these r's. So if these are perpendicular to r's and the angle between these r's is delta pi, so this angle will also be delta pi here. Okay, so the angle labeled delta pi between v1 and v2 is the same as between r and r. Hence the triangle in figure, this and this is similar. So this triangle is similar to this triangle here. So if the triangles are similar, so then the ratio of corresponding side of similar triangles are also equal. Then we can write that if we can divide delta v divided by v1. So if you divide delta v by v1, so this should be equal to, if you take this triangle here, which will be delta s divided by r. Okay. Now in this case, you can write uh, delta v, which is equal to v1 divided by r into delta s. Okay, so the magnitude average, the magnitude of average this velocity of the average the magnitude which is the average um, acceleration of the average acceleration during delta t is therefore. So if you just divide this you divide delta v by delta t, so this will be the average angular average acceleration here, which will be v1 divided by r, and which will be delta s divided by delta t here. So you just divide by delta t here, and now the magnitude a of the instantaneous acceleration. So a here is when limit delta t is approaching 0. So we will write that v1 divided by r and delta s divided by delta t. So that will become equal to, so v1 and so v1 divided by r and delta s divided by delta t is again v1. And because v1 is equal to v2, so we can say that it's v square divided by r. We just represent this by v. and and then because v is equal to r omega, so this will become r square omega square uh, divided by r here. So if you just cancel this r with r, so it will become r omega square. And this is obviously the a radial. So a radial in this case is r omega square here. Okay, so now we can solve a numerical example here, so that we understand the main idea of this whole exercise. So in a charming 19th century hotel, the an old style elevator is connected to counterweight by a cable that passes over the rotating disc, 250 millimeter diameter. So this is 2.5 meter is the diameter of this disc here. The elevator is raised and lowered by the turning the disc, and the cable does not slip on the rim of the disc but turn with it. At how many RPM must the disc turn to raise the elevator at 25 centimeter per second? So in this case, uh, what you are given that the given data. So you are given the you need to calculate this omega of the disk, or so that the velocity is equal to 25 centimeter per second here. This is our part A. And in the part B, what you need to calculate, uh, to start the elevator moving, it must be accelerated at 1 by 8 g. So A is given, which is 1 over 8 g, and this is A tangential. So what you need to calculate, what must be the angular acceleration of the disk? So alpha is unknown. And in part C, through what angle in radian and degrees has the disk turned when it has raised the elevator 3.25 meter between the floor? So in this case, you need to calculate the theta when s is equal to 3.25. Okay, so in the first case, we will use this equation here. V is equal to r omega, and obviously you are given velocity, which is 0.25, and then r is given, which is 2.5. So 2.5 divided by r divided by 2, so that will be the radius. And we need to calculate omega. So from here we will calculate omega, which will become 0.2 radian per second. And you can also convert this into, so if you multiply this with 60 divided by 2 pi, you will convert this into 1.91 rpm. Okay, so this was our part A. Now in part B, we need to calculate the A tangent, and you are given this equation here. So in this case, simple equation is A tangent, which is r alpha. So you are given A tangent, which is 9.81, 1 over 8 into 9.81, and again 2.5 divided by 2 is the radius, into alpha. So you will calculate alpha from here, which is 0.98 radian per second square. And finally you will calculate the angle here. So again, you just use this equation, s is equal to r theta, and again you are given s, which is 3.25, and again the radius is 1.25 into theta. So theta will become equal to 2.6 radian, which you can also convert into degrees, which will become 149 degrees here. Okay, so now we also would like to talk about the energy in rotational motion and moment of inertia. So now a rotating rigid body consists of a mass in motion, so it has kinetic energy. Now assume that the body is being made up of large number of particles with the masses m1, m2, and so on at a distance r1, r2, and so on from the axis of rotation. Now the mass of the ith particle is mi, and ri is perpendicular distance from the axis to the ith particle. Now the particle need not all lies in the same plane. Now when the rigid body rotate about a fixed axis, the speed vi of the ith particle is vi is equal to ri omega I, or omega. Now the different particles have different values of ri, but omega is the same for all particles. Otherwise, the body wouldn't be a rigid body. So now the kinetic energy of the ith particles can be expressed as, so the kinetic energy of just one particle in the body. So if this is our body here, so if you take this just one particle here, the mass is mi, and the distance from the center is ri, and then the velocity of the particle is vi. So the kinetic energy of this one particle will be equal to half m I vi square, and vi is obviously equal to r omega, so ri omega square. So this is the kinetic energy of this just one particle. But now we are interested to find the kinetic energy of the whole body. So the body's total kinetic energy is the sum of the kinetic energy of all its particle. So if you want to calculate the kinetic energy, it will become equal to half m1 r1 square omega square plus another particle m2, so which will be m2 r2 square omega square, and so on. So this means that we can just sum all the particle. So half mi ri square omega square. So in this case, we can just write this equation, because here half is constant. Only thing which is changing here is mass of the particle, and its position is changing. The remaining things are the omega is the same for all particles, and half is the same for all particles. The only thing which is changing is the position of the particle, which is r, and mass of the particle, which is mi in this case. So now the quantity in parentheses, which is this quantity here, is obtained by multiplying the mass of each particle by the square of its distance from the axis of rotation, and adding these products is called the moment of inertia. So this term is what we call is the moment of inertia here um, for this rotational axis. And now we can write the kinetic energy, sorry, the I, which will become equal to which is just m1 r1 square plus m2 r2 square, and plus so on. And then this is just equal to I mi r I square is our I here. We are just representing this by I, and the unit of this I, which is, you can see, is kilogram meter square. Okay, so if you have this I now, so now we can write the equation of kinetic energy. So kinetic energy will become equal to half and I omega square. So for the angular motion, the kinetic energy is half I omega square. Now what is this I physically? So the greater the body moment of inertia, the harder it is to start the body rotating if it is at rest, and harder it is to stop its rotation if it is already rotating. Now for this reason, I is also called the rotational inertia. So it is just the equivalent of mass in rotational motion. So if you consider these two bodies here, so in the first case, the masses are close to the center of rotation. So mass is close to the axis, small moment of inertia, and easy to start apparatus rotating. Now in this case here, masses are further away from the axis, so greater moment of inertia and harder to start the apparatus rotating. So this is how you you know about these systems here. Okay, so now this is again a very interesting numerical example. So a machine part consisting of three discs are linked by lightweight studs here. And what is the body moment of inertia about an axis passes through the disk A? So in part A, we need to calculate the I, which is about A, perpendicular to the plane of the diagram. And in part B, you need to calculate what is the moment of inertia about the axis through the center of disk B and C. So you can then calculate IB, BC. And what is the body kinetic energy if it rotate about the axis through A with angular speed omega 4 radian per second? So in part C, you need to find kinetic energy uh, about A, and omega is given, which is 4. Okay, so you calculate part A. Now, in this case, we are treating each disk as particles. We are not treating these disks as rigid bodies. So we are just treating these as particles. So in the first case, as you can see that if you want to calculate IA, so again, we will just use this equation I and MI RI square. So if you want to calculate the moment of inertia about this position here, about this position, so obviously MA is here, so it's R is 0. So this means that it will not contribute to the moment of inertia. The only masses which will contribute is this mass here and this mass here. So it will be just MI. So if we just take MB here, which is 0.1, and its distance, which is 0.5 and square. And similarly for the MC, which is the mass is 0.2 and the distance is 0.4 square. This will provide us with 0.057 kilogram meter square. This was our part A. In part B, we need to calculate IBC, because now the body is rotating about the BC, so the contribution of MB and MC will be 0. So it will be just uh, 0.3. And now in this case, we will always take the perpendicular distance because this is the moment of the mass. So the perpendicular distance between this axis and this mass is 0.4. So zero point 0.4 square, and that will become 0.048 kilogram meters square. Okay, finally, what we need to calculate in the part C is we need to calculate uh, kinetic energy when this omega is 4 radian per second, but we need to calculate it's about A. So kinetic energy about A is half I about A and omega square. So which will be, we know already IA, which is this 0.057, and omega is 4. So this is the 0.46 joule is the value of this thing here. Okay, now finally we will just discuss briefly about how we will calculate moment of inertia for different examples here. So the first one is moment of inertia calculation. So if a rigid body is continuous distribution of mass, as you can see in this case, like solid cylinder or solid sphere, so it cannot be represented by a few point masses here. So in this case, the sum of masses and distances that define the moment of inertia become an integral. Now imagine divide the body into element of mass dm that are very small. So in this case, what we will do, we will try to calculate the moment of inertia by using this equation here. We will take this small m that are very small, so that all points is in a particular element are it essentially the same perpendicular distance from the axis of rotation, so which is r, and we call this distance r as before. Then the moment of inertia is just will be integral of r square dm. So we will be just using this equation here to calculate the moment of inertia for different bodies here. So the first example here is that we want to calculate the moment of inertia for this cylinder. So if you see here, show a hollow cylinder of uniform mass density rho with length L. So inner radius is R1 and the outer radius is R2. So it might be a steel cylinder in a printing press. Using integration, find its moment of inertia about its axis of symmetry. So now if you want to calculate the moment of inertia of this specific example here, so the way we will do it, the density is given, which is rho, and you are also given R1 and R2, and you need to calculate I. So we know that I is equal to R square dm here, um, and for this we will be considering this a thin ring here, which is, you can see, is this dr, and the distance of this thin ring from the center is r. So what we will do, we will just write that the I is equal to r1 to r2. So r is the internal radius, r2 is the external radius, and what we will write here, so r square dm. Okay, so dm here is the mass, and the mass of this small element here, which is dr. So we can represent this by r1 r2, so which is r square, and dm is just the density times the volume. So density is rho, and the volume here is 2 pi r, which is the circumference into dr, and this is just a circular ring, and then we will multiply with L here to get the full volume of this cylinder here. So I will become equal to uh, 2 pi L density. So these are common. The only thing which will left inside the bracket, inside the integral, will become r cube into dr. If you just do this integration here, what you will get, uh, this equation here. And now this equation, if you just see for this specific cylinder, you can write that the L divided by 2, and this is R2 2 and plus R1 2. Okay, for this cylinder, the volume obviously of the cylinder is pi L into R2 square minus R1 square. So if we just pi and take this first part, so this part here plus this part here, and L is just the volume, and if you multiply volume with the, so it will just become density and volume, and then volume of the cylinder, and then R2 square plus R1 square, and then divided by 2. So now this we just end up with this equation here, and density into volume is obviously mass, so this become half m r2 square minus r1 square. So this become the equation of this cylinder, the hollow cylinder. So the moment of inertia of a hollow cylinder, by using this integration procedure, you can derive this equation here. Okay, and finally you will see that we can derive all these equations. So I will ask you to just go and try these different ways to calculate these different equations here. Now the final topic here is just the moment of inertia calculation using the parallel axis theorem. So now this is really important thing to know, that a body doesn't have just one moment of inertia like a mass. In fact, it has infinity many, because there are infinity many axes about which it might rotate. So as you can see in this case here, that if you consider this bait here, so it can have a moment of inertia about all these different axes. Okay, so but there is a very simple relationship called the parallel axis theorem between the moment of inertia of a body about an axis through its center of mass and the moment of inertia about any other axis parallel to the original axis. So now if you want to calculate the moment of inertia, if you know the moment of inertia, ICM is known. So if you say that the moment of inertia about the center of mass is known, and if you want to calculate the moment of inertia about any other axis, which may be at a distance of d from that point, so you will just use the parallel axis theorem, which is IP. In this case, if you want to calculate the moment of inertia about this axis, which is passing through the P here, which will be equal to moment of inertia about the center of mass plus mass of this body into d square, and d is just the perpendicular distance of the center of mass and this point P here. So it's just very simple example here. So if you consider a thin sort of sheet metal rectangular plate has a mass m, so mass is given, and the side of length a and b, so the side of this length is a and length another length is b here, and use the parallel axis theorem to calculate the moment of inertia of a sheet for an axis that is perpendicular to the plane of the sheet, and that passes to one corner of the sheet. Okay, so in this case, you need to calculate the moment of inertia, which is about this point P. So you can say that IP is unknown here. And for this specific case, if you go back, so for this specific case, you are given the moment of inertia about the center of mass, which is 1 over 12 m a square plus b square. So we know that ICM is given, which is 1 over 12 m a square plus b square, and we are asked to calculate the moment of inertia about the P. So we are given this is our ICM is given here, and you need to calculate IP about this point. So we can just use the parallel axis theorem. So IP is equal to IM or CM, center of mass, and plus MD square. Okay, now this D should be the perpendicular distance of this ICM and this point here, so which is this distance here, which we can calculate from this point here. So this is our B by 2, and this is our A by 2. So this means that IP is equal to ICM, which is 1 over 12 m a square plus b square, and then plus m, and d here is just uh, d square, so this will be d, so which is a by 2 square plus b by 2 square. So if you just simplify this equation, it will become 1 over 3 m a square plus b square. So that that's it for today. So if we just summarize the today lecture, so today we discuss about the about the angular motion in this lecture. So the value of theta in radian is equal to s divided by r. So theta equal s by r, or s is equal to r theta. Now the angular velocity is again the average angular velocity is delta theta divided by delta t, and the instantaneous angular velocity is d theta divided by dt. And the direction of angular velocity can be calculated using the right hand rule, as we discussed earlier. Angular acceleration again can be calculated using the average one, which is delta omega z divided by delta t. And similarly, we can calculate the instantaneous angular acceleration, which is d omega z divided by dt here. And again, we can see the positive and negative value of the alpha here. So if it is in the same direction is velocity, it will increase the velocity, and if it is in the opposite direction, so it's decreasing the velocity. And then we also discussed that we can also use these equations, which is similar to the previous case for the linear motion. Again, we discussed how to relate the linear and angular kinematics. So V is equal to R theta, A tangent is equal to R alpha, and A radial is equal to omega square R. We derived these equations. And we also derived the equation for the kinetic energy, that K is equal to half I omega square, where I is the moment of inertia, and which is similar to mass in linear motion. And then we can also calculate the moment of inertia using the integration procedure, which is I R square dm. Okay, and finally we discussed the parallel axis theorem. So if you know the moment of inertia at about the center of mass, you can calculate the moment of inertia about any other point in the body using the parallel axis theorem, which is this equation here. So Ip, which is the moment of inertia about an axis which is passing through point P, equal to the moment of inertia about the cm plus md square. So m is again the mass of the body, and d is the distance between the cm and the p. So that's it for today. Thank you.